Okay, so where did we end? I changed my laptop itself. I don't have last class. Let us just present something. Let's screen. Hmm? No, this is okay. This was last year course. The last time we were talking about it. Let it be. We'll start from here. No, I mean, now it's fine. I think. Okay, so how far we have been? That's better, right? So how far we have been? What we have done last class? I will also like to see your faces, Mokshi and Diksha and Nayan. I'll ask questions, so you may put on your mic and answer those. Okay. Actually, we change a bit arrangement a bit. These people are now off in class, and you people will be online. No matter. So how far we have come? What is the last thing we have done? Lagrangian, right? Can you tell me the last equation we have done? So basically, we are solving this equation. Let me start how to write this. So basically, we are solving Hartree-Fock theory, right? We are minimizing this value, expectation value of Hamiltonian, that electronic Hamiltonian, with respect to the set of one electronic orbital that we have chosen to generate the H psi naught or ground state, right? So psi naught is the single determinant wave function that is generated from single electron or single one electronic orbital. So psi I1, psi j x2, I'm sorry, psi n xn, right? This is the way we write. When you write this, basically this is a determinant. Only the diagonal elements are written, right? Okay, so this we have done already. This value before optimization we have derived. This is equal to sum over of I 1 to n chi I h chi I, right? And half of j chi I x1 chi j x2. This vertical line represents 1 upon r 1 to integral operator. This is chi I x1 chi j x2, right? This is the Coulomb terms, and I have the corresponding exchange term that will be chi I of x1, chi j of x2, right side. Now I have chi j of x1. Is it not visible there? Chi I of x2, right? Okay. So this all we got. This we also have written in a shorthand notation, just like you write 1 to n. In the Dirac notation, we have written HII plus half I equal to 1 to n, j equal to 1 to n, ij for the Coulomb part. For the integral exchange part, it will be ji, right? This is the Dirac or physicist way to write it. You can see that, right? Is it clear? Okay. So this also can be written. I'll introduce one more notation today, just to make you familiar. This is IHI plus half I equal to 1 to n, j equal to 1 to n. This whole thing written even in the simpler form, ij double bar ij. Again, this is also direct notation. This means that the anti-symmetrized product and anti-symmetrized integral. So this basically means that's same. The meaning is same. You can write separately. You can write combinedly together as ij double bar ij. This double bar represent first part Coulomb part minus exchange part. Right. This is the Dirac notation. So I have Dirac notation. You can write in terms of Mullikan notation, that's I equal to 1 to n. Mullikan notation is write as a square bracket is I plus half I equal to 1 to n, j equal to 1 to n. Here we write as ij. No, no, I'm sorry, this should not be written like this. Let me write, expand this. We write as I j j, right? And minus IJJI. So that's all we got. Yes. This what does this means? Let I take only one example. What does this mean? This term means you write expand this. This term, for example, means integration, double integration of chi I star x1, chi j star x2, 1 upon r1 2, chi I x1, chi j x2, dx1 dx2. It means that in the Mullikan notation, you write same index together, right? You see this one, this I comes with x1, this I star comes with x1. So I am writing I. This comes with x2, this comes with x2. I write with jj. Here you can see the exchange part, this will be jx1. Right? In exchange part, the orbital get interchanged. So I get chi j x1. I am writing as I j. Right? This will be j. So ij. This will be j x2. I get j x1. You get that? Yes, based on the orbitals. Okay, so these are just two different ways to write. They don't change anything. There is no change in physics. That's exactly same, just the way you want to write. Okay, when you do the programming, if you want, some of you want to do it, you find that sometimes this is convenient, that is convenient. All those integrals we have to generate. We have to write program for the integrals, and we have to put them in the proper location. It runs from I equal to 1 to n, j equal to 1 to n. Let's say I have n electrons, n equal to 100. Then you have those many combinations, right? So we'll talk about those much later. Okay, when we talk about little bit of programming part. So that's the thing we got. So we have, let me write this. We have this guy to be minimized with respect to, let us write it again. I have I equal to 1 to n, I h I plus I equal to 1 to n. There will be half here, j equal to 1 to n, ij minus ij ji, right? But as we discussed, this is not, we cannot directly minimize this because of this constraint which tells us that this guy I j, this follows the delta condition, right? And this for all I and all j. So that follows the delta condition. So you can just minimize this. We have to use Lagrangian. What is Lagrangian? When you have a constant, you put the constant as an addition to the original function and change the function. So basically, this is E0. We want to minimize E0, get delta E0 equal to 0. Instead, what we are doing here, we are writing a function, new function L, Lagrangian, which is also a function of the same orbitals, the parameters are not different, they're same. We write it as E0 minus with this delta condition, right? So I have not only one condition, delta condition, I have for all j. So for each constant, we are going to put one multiplier, right? And then we write is ij, sorry, this will be ij minus delta ij, right? Instead of minimizing this E naught, we are going to minimize. So now put delta of lambda equal to 0. That's the target, right? So basically what we do here, we have a function, we can't find the minimum of the function. We change the function from new old form E0 to new form lambda, and we are looking for a particular set of undetermined multiplier, right? We are going to find the set of epsilon ij such that the minimum of E naught and minimum of lambda is same. That's why we call it undetermined. We have to determine that. We have to find out the value of epsilon I such that these two functions, that is E naught and lambda, they have same minimum. That's all are important. We want to find out the minimum of E naught, but we can't. So convert this function to another function and choose your E naught such that the two function, to choose your this value such that minimum of lambda and minimum of E0 is exactly same. Okay. In this case, if I change I, j will be changed accordingly, right? So now lambda is a function of ij, but this ij are independent, right? You can change lambda, j will be changing such that, so you put this one such that this function become independent. For this function, I and j are independent. With this constant condition, we are taking care of dependence of I and j, right? So every time I and j is going to orthogonal to each other, and that orthogonality condition we are putting in epsilon I, right? You see, we are not really going to find the value of lambda. What are we going to find the minimum of lambda, such that minimum of lambda and minimum of E0 is exactly the same. That's what is the target, right? That's what we're going to do, right? Okay. So if that part is clear, now as I said that we have to write this yesterday, discussing, have to write this. So we are writing delta of E0. What is E0? I'll write it expressively. Sum over of I H I plus half of sum over of sum over of j, ij, ij minus ij, ji, right? Plus the other term, this guy, sum over of I and j.
Sir,
Yes,
actually, I understand the purpose. We cannot find the value of alpha, but we
hmm.
will find the value of minima of alpha, and then
Yes,
we will equate it to the minimum of energy, E naught.
exactly, exactly.
I don't understand this whole equation. Why you have subtracted delta ij and then in bracket summation of this? That is whole uh,
This you are talking about this part.
right. Yes, sir.
You
How
see,
it
what this part is basically zero, right? If you think this part is actually zero, delta, it came from this condition, right? So I can write like this ij minus delta ij equal to zero, right? Now we put this condition such that I and j are independent, right? Whatever dependence I mean, how I and j are dependent, they are orthogonal to each other. And what is the condition? This is the condition. Integral of ij minus delta ij equal to zero, right? The problem was we can't find minimum of E0 with respect to I and minimum of E0 with respect to J. See, when you are going to minimize this, what you are supposed to do? You are supposed to do this one. E0 divided chi I, right? This is what you are supposed to do. And this you are supposed to put equal to 0 at constant chi j. That's a partial derivative, right? When you have a function for two variables, when you put on the pen. I'm sorry. So, is it okay for you, Sri Shakti? Fine. So, what are doing here? This is what are actually are supposed to do. You can replace the volume. So this is what you are supposed to do, right? And similar, so this is the partial derivative. You would vary the function with respect to one variable, keeping other constant, and then you do this one. I mean, let's one condition can write j not equal to I. That's all about it, right? But problem is the moment I change I, j is also changed. Because j is not dependent. J is not independent of I. Right? Chi I and chi j must be always orthogonal. I hope up to that part it is clear. Now, what we do here, instead of minimizing this, we minimize that. Now, for this, I and j are independent. How it comes? The whatever change I have in I, right? Now you see this, the same change, whatever change that j will suffer because of change of I, right? Now let's say I is changed to I prime, j is changed to j I lost the internet connection. Hello? Can you hear me now? We lost the internet connection in between.
Yes, sir, it's fine now.
It's fine now? Okay, so that in the dependence between I and j, we are taking care of care here by putting additional zero term, right? Such that these two function has same minimum. Okay, so that's what we do. Let me erase this unnecessary cluttering things. So what we're going to do here, we have now this dependency epsilon ij minus delta ij, right? You have to do the variation with respect to this. We have done in the last class, the last one, right? So this we have wrote as term 1, this is term 2, this is 3, this is 4. The fifth one is just a constant, just 1 or 0. If you take derivative of a constant, that becomes 0, right? So here you do it. This fourth one we have done. Basically, we have done this part, delta of sum over I j epsilon ij, right? This, if you remember, this is equal to this epsilon ij is undetermined constant. I can take them outside. This is basically double sum 1 over I, 1 over j. I have epsilon ij, and that we have written as delta. Let me write it chi I, right? I'll expand this for convenience. So I get chi I delta. I'm sorry, this I not I. This is chi I k chi j. This is delta chi j, right? And we also have seen that since we have summing over all I and j, both term one is conjugate to another. See, first one is, let's say, a complex number x plus iy. Second part will be x minus iy. Bra and ket, they are conjugate to each other. So if you change the dummy variable of the last term, you make chi I as chi j and chi j as chi I. Then last term I get chi conjugate, bra become ket, ket become bra. You get the first term, right? So what we get here is sum over I j epsilon I j delta chi I chi j. I'm sorry, this is I, this is j plus complex conjugate. Okay, and then I ask you to do the first term. First term is also exactly the same. If you have done, well and good. If you have not done, then let me do this. This will be this term sum over I equal to 1 to n. Same way, I get delta of chi I h chi I plus, let me put a bracket here, chi I h chi, sorry, delta chi I. Right? I hope up to this part is it clear? You see, we are not differentiating Hamiltonian, right? The reason is we are not differentiating with respect to coordinate. We are differentiating with respect to the orbitals by I and j, right? H is the depending on coordinate R1. We are not differentiating with R1. We are not differentiating with respect to Rij or I, or I mean x1, x2, x3. We are differentiating with respect to the function itself. So only the function has to be differentiated, not the Hamiltonian, right? Now, if you write this, you can also from the same argument that we put here. What argument we put here? If we change the dummy variable interchange, you can see that this part and that part is exactly same. Yeah, I mean, you don't need to even change the dummy variable. You see, these are both same, right? So you take conjugate of that, you get this as graph function, this as get function. And Hamiltonian, all the Hamiltonian Hermitian operator, right? So H star equal to H. That's the definition of an operator that must be Hermitian. Okay, so you can also write that I can have I equal to 1 to n. I just can write delta chi I h chi I plus complex conjugate. Right? I don't need to write both the term. One term, knowing that one term is complex conjugate to another, we just write that. Right? Now let us go for the second term and third term. What is second term? I have delta 2, we write is uh, this was half sum over I equal to 1 to n, j equal to 1 to n. Let me write in now in terms of this function. So I have delta chi I chi j chi I chi j. Right? We get four terms. We get here chi I delta chi j chi I chi j plus chi I chi j delta chi I chi j. Sorry, there's a this should not be there, right? Chi I delta chi j. Right? Is it okay? There are four terms from the Coulomb. Right? Each functions we have to differentiate. Okay? Now let us write it explicitly. We'll expand this in terms of integrals. I, j, this is double integral delta chi I of x1 chi j of x2 1 upon r1 2 chi I of x1 chi j of x2 dx1 dx2. Right? Is it okay? Just I am writing this in terms of integral. As I said, all the notations are important. Okay, so you have to get used to whenever I write one notation, you should understand what exactly you are writing. Okay, that notations must be there in your head. So that is the first term. Second term you write as I'll put one bracket here, right? Because half is in the bracket and sum is in the bracket. I write double integral of pi I x1 delta chi j of x2 1 upon r1 2 chi I of x1 chi j of x2 dx1 dx2. Write all the four terms. These become delta chi I of x1 chi j of x2 dx1 dx2. These become I'm sorry, this will be chi I of x1 delta chi j of x2, right? Now we can put the dummy variable interchange. You can see that this term, the first term and second term. Let us analyze this. If you think about the first term and second term, if you change I into j or x into 1, I mean 1 into 2, right? Basically both are same, both are dummy variable. X1 and the 1, 2 are dummy variable, right? Because we are summing over x1, x2, we are integrating over x1, x2. So which one is x1, which one is x2, that really does not matter because we have all the sum, right? Similarly, we are also summing over all I and all j. After summing up, which one is I, which one is j, they don't matter, they're same, right? So, if you notice that for the dummy variable interchange, the first two terms are exactly same. Is there any doubt? I am not going to write that. It's my point. I don't want to write that, but we must understand that these two terms is exactly same. You make x1 as or I as j. The first term you keep as such. Second term you make wherever you have I, you put as j. Then second time you get chi j x. I mean I as j as well as x1 into x2, 1 into 2. So second time you get chi j of x2 delta chi I of x1. 1 upon R21, right? R21 is exactly same as R12, it's a distance, right? Chi I of x1, this will become chi j of x2, and chi j of x2 will become chi I of x1. dx1 will become dx2, dx2 will become dx1, right? So first two are exactly same. Similar argument you can put and show that the second are also exactly same. Yes. Yeah, we have to make the stars. Yes, right. We have to put the stars. I forgot to put the stars. All will have stars. Yes, that must be there. These are conjugate, right? So first two are exactly same, and last two are also exactly same. Let us write that. So I can write as half sum over I, sum over j. This will become double integration of del chi I star of x1 chi j of x2 1 upon r12 chi I of x1. Just write it down. Just write on your looking at your note and write, right? So then this term, the first two are exactly same, so I can write 2 here since they are same. Second, third, and fourth are also exactly same, so I can write 2 here, and that will give me chi I star of x1 chi j star of x2 1 upon r12 delta chi of I of x1 by j of x2 dx1 x2, right? So you see we got this part common. The 2 will be common. If you take it comes out, it cancel that half. So all I get I j. You can see this we write as, let me write it again, delta chi I of star of x1 chi j star of x2 1 upon r12 chi I of x1 chi j of x2 dx1 dx2 plus, right? Easy, just need to write it down, right? There's nothing difficult in it. Just with the patience you have to write it. Yes.
Last, previous step to last step.
We had two, right? We have half, we had two common,
Just cancel.
just cancels. The constant can always cancel, right? It's not a function. Now, can you tell me the relation between these two terms? The last equation. What is the relation between last two terms? They are complex conjugate. Is it okay for everybody? For the other side, Mokshi Diksha,
So,
is it okay? The last terms are conjugate to each other. This one and that one. This
yes,
one and this one are complex conjugate to each other, right? So if that is the case, then I can write only one term. So I write I, J, right? I'll write in the old fashioned Dirac notation, chi I, chi j, chi I, chi j plus complex conjugate. Right? Let us go for the. I hope this part is clear. Srisha, this is fine. Is it fine for you? What about you two guys? That's fine, right? Now let's go for the exchange term. Right? What is exchange term? So basically, I'm going to do del of 3. This will be, let me write in the same way. I, j, there is a half term here. You get integration of chi I, that was delta, right? Delta chi I. I'll write directly, or let me write in the old version. I get delta chi I, chi j, right? Chi j chi I plus chi I delta chi j chi j chi I. This is wrong, this is wrong, this is not correct. This third term I did not write correctly. This will be chi j chi I. This will be chi j delta chi I. Right? Same. You have four different variables, right? Two with star, two without star. So we have four terms what after differentiation. Right? Now I will give you a task. Using the same argument, you can also show that this is exactly same as I write this with the same argument of putting dummy variable equality of the dummy variable. This can be showed as this is equal to half sum over of I, sum over of j, delta chi I, chi j, chi j. Only thing is half will not be there. I will give you a task. You prove this. Right? There's nothing to worry about it. It's just bland expansion, expand every term in terms of integral, and for the first and second will be same, third and fourth will be same. Same we have done for the Coulomb, same we do for the exchange, right? You will find this is exactly, this is also give you one term, not only one term, this also give you, along with this, we have plus its own complex conjugate that we should not forget. That's the four things we are going to get. So please do this. This is not difficult. They have to just expand all the four terms in terms of double integration and change wherever you have I, J, change what suits you, right? We can change that because they are integrated over the x1 and x2. They are also summed over I and J, right? So both I and J are dummy variable. X1 and x2 are also dummy variable. 2 and 1 are also dummy variable. You can interchange them. Okay. So if now we have all the terms after derivative. We have done 1, 2, 3, 4. Fifth is constant, this anyway is 0. Right? Now let us write them together. Okay? I write again in the integral form. So what we're going to have here is putting them together. Therefore, I get here integration of delta chi I star h sum over I equal to 1 to n h 1, basically they are same 1 2 whatever you can write, you can call I also, chi I dx1. Let us write it more explicitly. This will be x1 h1 chi of I x1 dx1. That is the first term for the one electronic part, right? And then second electronic part, what we got? Sum over of I, sum over of j, double integration of delta chi I star of 1, x1, x1 chi j of x2, 1 upon r12 chi I of x1, this must be with a star, chi j of x2 dx1 dx2. This is the second term. Third term, if you don't forget, it comes with a negative sign, right? It's an exchange term. While doing the expansion, I did not put the negative, right? But you can, a negative can also be always taken as common. So just put the negative here, right? So we can put there, I think I put negative, right? Where is that? No, no. Where did I put? Not here. There I did not put because I don't need to do that, right? Here, this negative, right? That negative, now we are writing. See, I am writing this as term 2 without negative, right? So I can here write here a negative term. This is sum over I, sum over of j, double integration of del chi I star x1 chi j star x2 1 upon r12 chi j of x1 chi I of x2 dx1 dx2, and I have plus this term sum over I, sum over of j. Let us split here ij. I constantly saying here this is double integration chi I star x1 delta chi j x1 equal to 0. Sorry. For each, I have complex conjugate, right? This term has a complex conjugate. This term has a complex conjugate. Every term has a complex conjugate, right? So I can write the complex conjugate together. That's how we write the complex part, right? This, since we are minimizing it, we are setting this equal to 0, right? Why are setting? Because we have put this equal to 0. So from there, we got this. This is what we have to minimize. So we are putting this. The way of writing complex number is you write real part together and complex part together, right? Any complex part, that's the way to write. All real part you first write, and all complex part you write second with imaginary. Right? So like I have x plus iy, or 5 plus 6 plus 10i plus minus 20i. So all I part we write together, all real part we write together. That's what we did, right? First term is the first all four. 1, 2, 3, 4. 4 are the real, not real part. I can't say which one is real, which one is complex, but first one is the conjugate of the second one. Right? Now here is the thing. If I have two numbers which are conjugate to each other and their sum equal to 0. So what is the condition? What I am asking you, basically it's saying this. I have a plus a star equal to 0. So what is the condition for this? What condition will satisfy this? You see, when I have two numbers, forget about the complex number, two real number, let's say a plus b equal to 0. What does it mean? Either not inverse, negative. Don't say lose or inverse and negative are different, right? Negative you if you like add them it becomes 0. Inverse you multiply them become 1. They are entirely different thing. So one condition is a equal to minus b, right? Another condition is a equal to 0, b equal to 0. Right? If two numbers are complex conjugate to each other, then I cannot write a equal to minus of a star unless they are not anti-Hermitian operator. That is also possible when A is an operator or matrix which is anti-Hermitian. We come back to the point when we talk about Hermitian, non-Hermitian, or anti-Hermitian. But basically, one A is plus a star. Add complex conjugate will give you equal to 0. In this case, A is not equal to minus a star. There's no way to prove that, no way to say that A equal to minus a star. Real part should be 0, complex part also should be equal to 0. Both are 0, together equal to 0, right? 0 means 0.
Complex part is there. IB minus IB will come.
Tell me again.
Here, A plus A star is equal to 0. If real part is 0, means IB minus IB will come. Conjugate means A plus IB.
Yeah, but there is A and A star, they are same, only with complex conjugate. So what I mean that I have something like, you see, x plus iy, x minus iy, right? These two are not same. They are complex conjugate. If these two has to be same, then it means each one is equal to 0. You get? If you add them, you are saying that plus I and minus I will become 0. Right? This, so if I have this plus this equal to 0, it means y equal to 0. X is anyway equal to 0. Did you get my point? You see, you just add them. I will go for our logic. I'll add these two together. I have x 2x plus equal to 0. What does it mean? X equal to 0. Right? You put there x equal to 0 in one of both of them, it become y is also equal to 0. You see, cannot say x plus iy is equal to x minus iy. Can we say that? No. So this condition does not satisfy. If they are same, then real part are same and also the imaginary part are same. I'll give another example to avoid your confusion. Let's say I have two complex number a plus ib equal to x plus iy. Now what does it mean? It means a equal to x, b equal to y. Complex part are same, and real part are same. If I write this is equal to, so basically I am writing this was there, a equal to plus a star equal to 0. Right? So I write this plus this star equal to 0. In that case, each part will be equal to 0. Write the equation, you get the answer. What is the confusion?
No, sir. Are you telling 3i minus 3i? If we are having 3i minus 3i, then it should be 0.
No, I'm not telling that. Minus 3i and 3i are not same. They are conjugate to each other. But when they are same, then each part will be 0. You understand? I'm not telling 3i equal to minus 3i.
No, no, I am asking a is not equal to
Minus 3i. So we cannot hold that. I am telling like a plus ib equal to x plus iy. They are conjugate to each other. Adding two terms which are conjugate to each other will give you 0.
a plus I, if we are multiplying to conjugate use a plus ib into a minus ib, actually it is equalized to a square plus b square.
Yes, yes.
In that way, during that time, we are multiplying b into b square we are putting. We are not specifying it in a different way. B square we are putting. So, my question is,
Hello. Good afternoon. Can you tell me quickly what happened? No, no, no. I can't have a class. Please don't call me right now. Yeah.
we are
I have a complex number. Let's say a plus ib. I mean a plus ib. Right?
multiplied by a plus ib.
Not multiplied. I'm adding it. Adding its complex conjugate.
Okay, a minus ib.
A minus ib equal to 0.
Okay, sir. Here ib minus ib is getting cancelled.
So A is also
A
0.
is equal to 0. So
In that,
it is not necessary that b should be 0.
it is also necessary to B should be also 0. That's what I
That's what I
if you think about real number A plus IB, A plus B equal to 0. Right? Here condition is either A equal to minus B or both are equal to 0. If it is complex, I cannot put A equal to minus B. That I cannot put. So the other condition must be satisfied. Each individually must be 0. Understand? That's how that is why I am putting the logic. Real number and imaginary number is the real number is real part of the complex number. Right? So the real part is anyway 0. The complex part also must be 0 to satisfy this condition. Right? No matter. So even if I go with your argument, the first term is equal to 0. Understand? So I have one part and another part which are complex conjugate to each other. So I can write the first term equal to 0. Right? So with this logic, what I can write here, we can always say, so therefore from here you put a logic, you put implies that integration of delta chi I star x1 h of 1, there is some, right? Chi I of x1 dx1 is I greater than ij I'll put again the same way, delta chi I x1 star ij x2 on upon r2 ij of x1 chi I of x2 dx1 dx2 plus there's integral, yes, that must be. There's a minus, just write one another term, right? Minus sum over of I, sum over of j, this was sum over of I, um, delta chi I star x1 chi j of x2 1 upon r12 chi j of no, this is not correct, right? This is not correct. This is not correct. This was I and j. They don't change. So this was I, this was j. In the exchange term, I have x1 by j of, I'm sorry, by I of x2 dx1 dx2 minus sum over of I, sum over of j, yeah, epsilon ij, there is integration. This is dx1, right? Is it okay? Now look at this term. Everywhere I have sum over I. Can I take sum over I common? All the terms I have sum over I, right? It also have sum over j part, some part. But I can take always sum over I equal to as common, right? I can do that. Okay. So in the next line, what I'm going to do here, I'll omit this sum over I and make them as common term. Is it clear? I has gone, right? From all I have put it sum over common, right? Sum over x I over 1 to n. That is there in all terms, right? So I'm putting that as common. Okay. Now what does it mean? Sum over this is equal to 0. Right? I have to see I have similar condition. A plus B plus C plus D plus E equal to 0. The condition is either they are linearly dependent, means part of them is equal to minus part of others. Then it becomes 0. If A plus B equal to 0, one condition is A equal to minus B. A plus B plus C equal to 0, one condition is A equal to minus B plus C. Or any combination. That's the thing we can put, right? But there's not a really physical way to prove that. How can I prove that one term is negative others? Each will have the individual values. Electron can occupy in I equal to 1, that is first orbital, I equal to 2, that is second orbital, up to I equal to n. All n orbitals it can occupy. So there is no way that we can say one term is equal to minus of other term. It is physically unacceptable. So what is acceptable is every term is individually zero. Right? So I can remove that sum over and just write this equal to 0. Right? So what I'm going to do here, just remove this term. Again, I'm not writing it, feeling it a bit lazy. I'm not writing it, I'm just writing this equal to 0. Right? Is it fine? Now I'm going to little bit modify again that epsilon I is a constant, right? I can, and this whole thing is also a constant, it's an integral. It is a definite integral. Every term, every integration is a definite integration, right? It starts from the limit. If you're doing atomic calculation, it will start from 0 to infinity. The moment you put the limit, the definite integral, it becomes a value, a number. Right? So epsilon I is also a number, undetermined multiplier. A number that depends on I and j. For each I and j, I'll get different epsilon ij values. Each one is a number. So what I can do here, I can just write, instead of writing it here, I can just write this whole thing, put a bracket, epsilon ij equal to 0. I hope that is clear. The reason I am telling here, you have to also be comfortable with this. Inside the numbers always commute. Operators not necessarily commute. So since they are number, I can easily exchange their position inside the equation. Right? Is it okay? No, I have a mistake here. What is the mistake? Can you find the mistake?
So D is not, the differentiation is not.
Differentiation must be there here, right? Here it is differentiation. So this will be delta of chi I. Right? Yes. Why is put? We have put negative. That also started negative. No, we have to put a negative. There's a mistake not there. There's a mistake here probably. This we start with negative. You look at your Lagrangian. Look at your Lagrangian. We put negative there. I'm sure. No, this should be negative. I'm sorry, you just put it negative. Again, it does not really matter, but as a convention, we put a negative. You see, Lagrangians are put to get some of the things that is actually predetermined. No matter. So that's why we are putting negative here. When you put the Lagrangian, be sure that we are putting in negative sign. Right? Now I can write this in a bit modified way. Let me write this. Yes.
Sir, can
Can you explain what you have done in the last term related to?
Here.
Yes, sir.
You mean here? You see,
Yes.
this is a number, right?
Yes, sir.
This is integral, a definite integration, which is also a number. So all I did is just instead of writing 2 into 3, I have written 3 into 2. That's all.
Just interchange of the terms.
Yes. The numbers always commute. Yeah, Divya, is there any question?
Okay,
So numbers always commute. So I just interchange it. This is done just to make you see what we can do in the next line. Every derivation, every line of the derivation should tell us what should we do in the next. So you can see that what I'm going to do here is, yes.
Nothing, sir.
I mean, you are asking him something. I think I know a little bit more than him, so you can ask me. Yes, what is your question?
After the negative integral.
Third term, yes, definitely integration will be there. Not only one integration, there should be two integrations. Yes. Sure. Good thing. That must be integration, yes. Without integration, that doesn't have any meaning. Okay. Right? So that's all. Now what you see, what we're going to do is next is we just write is in terms of, let me rewrite this term again. delta chi I. We are going to write this as a integration of delta chi I star x1. I put sum here because this is I, right? So I can move sum inside. There's no sum over I has gone. So I can put sum here. I write j star x2 1 upon r1 2 chi I of x1 chi j of x2 dx1 dx2. Same thing I'm going to do the third term. I get integration of delta chi. There's another integration, right? This integration I should not forget. There's another integration for dx2, right? So I have here as integration of del chi I x1 sum over of j integration of chi j star x2 1 upon r1 2 chi j of x1 chi I of x2 dx1 dx2 plus sum over of, I'll write this again same fashion, not plus, this must be minus. I'll write the same way with a minus. I write as delta chi I of this will be star. Right? Please, you don't make mistake, right? I have sum over of j chi j of x1 dx1 epsilon ij equal to 0. Let me put a bracket here. Right? Is there any doubt? You see, this we can be do because the sum over j, sum over is not equal to y. So I can put whatever is not under the sum, I can put outside. Right? Now, I have done this on a purpose. The purpose is, you see, integration of delta x I star chi I. That's there for all the terms to the left side. I can take that out, meaning that I am differentiating or I am unprojecting. Right? There is something called projection operator. Projection, not operator, projection. Projecting means you multiply it with a vector and do the integration. So what I mean that if I have a something like this, let's say I have an operator, A operating on G will give me another function, let's say F. The projection means, let's say I'm projecting with G star, projection means multiplied by star, P multiplied A, G, and then integrate dx. This can be written as G star F dx, right? This I hope you know, is clear, right? I have an eigenvalue equation, I have an operator equation, an operator operating on a function, give me another function. I can do this always, right? You multiply by complex conjugate of the first function and take the integration. Right side also you have to do the same thing. This equality hold for any cases, right? So what I mean that I can write this equal to this. Similarly, this must be equal to that. The way of doing it is called projection. Projecting G over Ax or over F. I got the second equation. If I unproject, I get the first equation. Right? Yes, Sri Shakti. Fine? Everyone is fine with this? So I can remove integration over xi and delta x chi I star. That part can be removed. Right? You look at this equation, if I want to go from here to here, I have to remove this and this. I get this equation back. So same way, I can also do in the reverse way. Reverse will also hold. So this can be written as h1 of chi I x1 dx1 plus this is gone, right? This integration of that projection is gone. I get sum over of j integration of chi j star x2 1 upon r1 2 chi I of x1 chi j of x2, right? dx2 dx1 has gone minus sum over of j integration of chi j star x2 1 upon r1 2 chi j of x1 chi I of x2 again to dx2 minus this one. This has gone. I get sum over. I write again this. I write this is first. This is first. I write epsilon of ij sum over of j chi I of I'm sorry chi j of x1 equal to 0.
The dx
dx1 is gone, right?
plus
Which one? First. Look at just try to compare these two. The d chi 1 is the projection, right? D chi 1 is actually in our example g star. You see, a function, derivative of the function is also a function. Right? Think this way. If any function, if you take the differentiation, you change the function. So derivative is an operator, right? Another function. So del chi I star x1 is a function, right? I have deprojected. I'm projecting, now I'm projecting it to get my original equation back. So I can do this, yes. You have any doubts? Who is one?
dx
Yes, you're right, yes. This one must not be there, yes, of course. No. On the flow I'm writing. That dx1 must not be there. Yes. I am thinking that you are asking for that d. I have ordered the book. So now you see this we have a simpler equation, right? We write it even more simpler way. Let us write it again in a simpler way. So I'll write this as H1 is an operator, right? I'll write this as sum over J integration of chi J star x2, right? 1 upon R1 2 chi J of x2 chi I of x1 dx. Right? I hope you agree with this. All I did there, just again, these are two functions. They commute. I am writing just interchanging them and rewriting. Right? In the same way, I can write this minus sum over of j integration of chi j star to x2 1 upon R1 2 chi, right? J of x1 chi I of x2 dx2 equal to right side as right. Let us move the last part right side, sum over j epsilon ij ij x1. Right, there's a mistake I did. What is the mistake? This is chi I. No, I did not do a mistake. I want to do something else, then I forgot. This is of x1. Right? You see, what I actually wanted to do is, let me write this way. So, let me write this way. You see, this term, what is there? Like, try to let understand this. This chi j x2 chi j2. What does it means? It means the probability of finding electron 2, right, on chi j orbital. Right. So this, if I multiply this term again, chi I1 star, I get two probability, one as x1, one as x2. They are repealing by 1 upon Rij. So this term is called Coulomb term. In the second one, you see left side is this, right side I don't know what is that. Left side, electron 2 is on orbital J. Right side, electron 2 move to orbital I. Right? So we don't know what is that. This is called exchange term. Okay, so this whole thing can be written as H1 H of 1 plus I'll write sum over of J. Since all are J, let us write as J of J minus K of J. Right? Then what I do, I'll write chi I of x1. I'm writing this in a red color for a reason. Right? What it means? It means J an operator which will operate on chi I1 will give me this term. Do you agree? Do you understand? JJ is an operator which will operate on xi will give me that. Just a multiplication. Right? On the other hand, Kj, what Kj will do? It will operate on xi orbital and replace xi, chi I with chi j and chi j with chi I. Yes, what is the doubt? Hmm? That's what. The Kj will say, an operator says that when it operates on chi I, it give me that term. How to give it that term? Chi j will be chi j as such. On the right side of R12, it will exchange the orbital. Right? This is needed because in the according to Pauli exclusion principle, we need to interchange the orbital, right? And everything in quantum mechanics we does, every job we does do in terms of with a operator. So I'll define an operator Kj. What it will do? It will operate on chi I and give me chi j star x2 1 upon R12 chi I x chi j x1 chi I x2. That's all. That is what we're going to do. Right? Now, you see what does it look? Left side, everything it depends on electron 1. Right? Everything has only one index. So left side I can write this whole guy full term inside the bracket, I can write as f of 1 by I of x1, right? Right side what we get? We get j of epsilon ij by j of x1. This is the famous Hartree-Fock equation. All we got. Not very good looking. Right, what? That's all we got. What is the problem with why did I say it's not good looking equation? You see, left side is fine, right? I have an operator operating on a function I. What do I expect? Same function. I should expect same function back with a number. Right? What we call as eigenvalue equation. Eigenvalue equation are easier to solve. Basically, you want to solve that. But what right side we got? We don't get same function back. We got some other function. And we don't get one number. We get a sum over a set of numbers. Right? So this is not that what we want. We can't solve this. What we want basically something like this. F of 1 chi I x1, we get something like, we want to get something like this is equal to epsilon I chi I of x1. That's what we want, right? So this is called non-canonical Hartree-Fock equation. Non-canonical. Non-canonical Hartree-Fock. This is called canonical Hartree-Fock. Canonical means well known, which is familiar. Right? What all we need to do now from non-canonical Hartree-Fock, we have to now convert into canonical Hartree-Fock so that we can solve it. Right? So after 2 days of derivation, this is why we got which we cannot solve anyway. Okay, we have to again transfer into a canonical form. Right? Let us stop here unless it becomes too heavy. But all of you must do the derivation once. Okay, I first thought of not doing the derivation. I thought of starting with this. The derivation I did not plan to do this time. Last time when I was teaching with her and this Ayan and Mokshi and Diksha, I did that time. So this time I thought I'd skip this part. Right, but then you people join. So it's better to at least one time you should do this derivation. It does not have much of mathematical difficulties. All you need to have is peace of mind, patient you should do. You may make a lot of mistakes like I was making, but that's part of it. A lot of mistakes while writing, but you have to be careful. You do it once this derivation up to non-canonical. From there, we are going to move to the canonical. Before Tuesday, you read a little bit of matrix transformation. Everything you are going to write in terms of matrix. And again, this is not only you are not only unable to solve this. We can solve this obviously, but only for the atom, not for the molecule. Right? Even canonical Hartree-Fock equation is good for atom. For molecule, we can't even solve this. We have to move towards something called Ruthan theory. Right? That we will talk about in the next class. Okay, there will actually our quantum chemistry will start. We have to have basis set, different type of basis set, everything will come there. But let us stop here. Any question from your side? Mokshi, Nayan and Diksha?
What? Excuse me, sir. Sir, the second last equation where you introduced this J and KJ operator.
This operator is
Yes, sir. Sir,
yes.
I am not completely convinced about this term chi
Hmm.
I to
Hmm.
x1 we are using. Because if I'm relating it with the above term,
Hmm.
sir, the kj is going to change only the uh, orbital, sir. It will
Cage is
chi.
going to change, yes, only the orbitals, yes. Let us write it.
Sir,
Since you have raised this question, let us write it. What I write, said Kj operating on chi I, right? This is going to give you, how did I write?
If you execute xj,
Yeah. So it is going to give you this chi j star x2, that is anywhere there. I have 1 upon 2. Now what this is going to do, this is going to make me chi j of x1, and you see inside I have chi I, right? Inside, so this, I mean inside I have chi j, this chi j was there. So what will do, chi j will become chi I, and it's what I'm doing. Chi j of x1 is chi I of x2.
how does x2 came? That is my point.
Pardon? This kj, whatever is right side is there, it's just going to exchange. I have chi I x1, right? That is going to make me chi j x1. Here I already have this term. This you should not forget. This was there. I mean, let me write it this way. This was already there. This was already there. This will be there, chi j. Right side I have chi j x2, right? It is going to make me chi I x2. I had chi I x1 is going to make me chi j x1.
Okay.
So whatever is there, right side to 1 upon r1, 2 is going to exchange that, exchanging the orbital,
Karna on.
right? So if you have a problem, then you think this way. This chi j operating on chi I mean this. That is the definition of chi j.
Okay, sir. I got it. That it will be operated on the right side of the operator only.
Exactly. Right side, whatever orbital I had, it's just going to make it I to j j.
Okay, sir. Thank you.
See, this is needed. This is very much needed. Unless we have this, we don't have exchange. Yes, Divyani. Right? Okay. Any other question? Okay. If you don't have any question, let us stop here. Tuesday we'll meet again. You want to write some? Mokshi, you have yet to finish the writing?
Hmm.
Are you yet to finish the writing?
Yes, sir. Mokshi has still something to write.
Okay,
The
okay.
last line which you.
Yes, 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 yes.
Sir, done.
Okay. Then we'll see on Tuesday. Yes, Nayan, you are asking something?
No, sir. The confusion is clear.
Okay, fine. Okay, so derive this equation once more time and read little bit of matrix transformation.
Okay, sir. Sir,
Yes.
Sir, I have my GATE exam on 15th and net on 28th.
Okay,
So
you will not be
I'll
able to
try.
attend
No,
those.
no, I will try to attend the classes.
Okay,
Um,
15th is Saturday, right? 18th is
yes.
Tuesday. Okay, not a problem. You go ahead with your exam.
Sir, when you will, from which book you are referring? Zabu?
I am preferring Zabo, mostly Zabo, but not in the order. You see, Zabo is an advanced book, right? Uh, Derivations you'll find everything in Zabo, but I'm not following the order of Zabo. Right? My plan is to first do the derivation of non-canonical artifact theory, then go for the canonical. From canonical, we have to, yeah, from canonical, I first thought of doing the spin integration. We are still on the spin orbitals. Every
Yes.
orbital has one spin, either alpha or beta. Right? We can do the spin integration and remove the spin part. After doing that, I'm planning to go for the Ruthan equation. Right?
I
R
will
is
attend the classes. Actually, last class, I was
hmm,
not able to follow all the material as I was applying for the fellowship. Roy sir told me to do it.
okay.
So today was little not familiar, but I'll see.
You read. If you have
I'll
a doubt,
attend.
just write to me. Okay.
Okay. Right now, I'm just trying to prepare for the exams.
Fine,
Mm,
fine. That's fine. That's fine. Prepare with. Okay. We can again next year also. I am planning to continue this every year. Okay. So if you are missing this year, next year we can catch up.
I will try to
Yeah, sure.
manage. Okay.
Okay
Thank you
then.
so much, sir.
See you.